Multivariable Calculus 12.5 Day 2. We're now on our third video, wrapping up the lesson. This last example, finding the angle between two planes, really is finding the angle between the two normal vectors. And finding the angle between two vectors, we use a dot product. That's where we left off. Solving for cosine, we can very quickly come over here and then just find an inverse cosine. And we don't even have to allow our radicals to be reduced. You can see I just pretty much typed this in. It looks like it's about 94.731. So about 94.731 degrees. And again, you just have to find the length of these two vectors. Through the Pythagorean theorem, you can see we'd have the square root of 49, which is 7, and this is a radical 12. Solve for cosine, take an inverse cosine, and then you're good to go. One last problem that we're going to take a look at. The intersection of two planes. The intersection of two planes is going to be a line. Whenever you open up a book and you see two pages crossing, you can see that where they're touching would form a line. But what I'd really like to show you here is this great picture. If you have two planes, you can see what's happening. I'm running my cursor right over this right here. You can see these two planes are much like you could see the two pages coming together around this line right here. But notice the direction vector of this line. You have your two normal vectors, and if you were to take their cross product, what we're seeing right here with that u is equal to n1 cross n2. That's really what we'd like to hold on to here. So when they say find the line of intersection of two planes, what they're really getting at is, can you get a point of intersection, and can you then also get that direction vector? So we've talked a lot about the vectors right now. Let's take a look at plane 1. With plane 1, the first normal vector is going to be looking at these coefficients 3, -6, and -2. Likewise, for our second plane, if we were to look at these coefficients, we could say that we have a 2, and a -2. Now, here's a little trick that you're going to see many professors do. Look, you could divide something out. We could have done this earlier too in the previous problem, honestly. And you could divide out a common factor. Now, you can think, now wait just a moment, that vector now is half as big. But honestly, what we're really getting at is this much. If we're just looking for that cross product, it doesn't matter if n1 or n2 is going to be noticeably shorter. You're still going to get a cross product vector in the same direction. And that's the thing that we're most looking for too. So do you have to do this, especially in light of having a calculator? No, you certainly don't. But I really need to tell you, that's what you would see on many college campuses. If you were to cross these two right here, you would get the direction vector. The direction vector of that line would be 8, 1, 9. Now, if your direction vector happens to be larger, that's okay too, isn't it? All right, well, from here, that's just one side of it. You could really, fall back and say, wait a minute, when I'm getting the equation of a line in space, what we undoubtedly are going to go back to and hold on to is this. We have this parametric form, and what's delightful right now is a direction vector. You have an A, B, and a C. What you don't have is a point on the line. And, it's at this point where perhaps maybe we could use these two equations of our planes and utilize them to find out through elimination if we could find a point of intersection. So as we're looking right here, notice I'm selectively not dividing by 2 everywhere here. I'll tell you why. As I'm looking, hoping to eliminate something here, I'm seeing a negative 2z and a negative 2z. So I'll tell you what, we could very quickly get some help here. We could say, you know what, I'm going to multiply this equation, the second equation, by negative 1. And that would leave us with negative 2x minus a 2y, and then a plus 2z, and that would equal negative 5. And that will cross out here. We'll have an x minus an 8y, and set that equal to a 10. Now it's right here where we could very well think, well, that wasn't very helpful at all, is it? But I'll tell you what, even though we haven't gotten down to a point where we could very simply find an exact x and a y, I'm going to choose x equals 10 and let y equal 0. That would make this equation true. Now remember, I just eliminated one thing here, and I know that 10 and 0, x equals 10, y equals 0, makes this equation right here true. I also want to make both of these up here true. So look, I'm going to right now choose either one of these. Sometimes kids will say, well, this one looks a little bit easier, I suppose. Honestly, they're both the same. You could choose either one. If you were to let x equal 10, let y equal 0, now we could go ahead and solve for z. So this is 20 minus 2z is equal to 5. And I can subtract a 20 from both sides, and that would be negative 15. And then I'd get z is equal to 15 over 2. By the way, if you would have, I'll leave it for you to check, if you would have said, wait a minute, I want to plug these values in here into this other equation, I've got some really good news. You'd get the exact same answer. That's the beauty of having this as a, a system of equations. So what we're seeing is we found a point that's on both of those planes simultaneously. What we're doing then is we're finding that that's actually the point that's on the line that's satisfying both at the same time. In other words, that's your x naught, y naught, z naught. So what's your equation? Well, you'd have x is equal to 10. Your a is an 8, so it's 10 plus 8t. Your y is y naught, and that's a 0. But your b is a 1, so that's 1 times t. And finally, your z is z naught. That's your 15 over 2. Plus, well, your c is a 9. That's 9t. So we get the equation of a line, and this is the symmetric form of that line.